Section 2.4 and 2.5 again. Today, we study how to find horizontal and vertical asymptotes. Take a review first. Number one, a limit of this form is called an infinite limit. A is a finite number. The limit is an infinity. Here is one example. This is a sketch of this infinite limit. X approaches A from the both sides. This is a both-sided limit. Function approaches negative infinity. So near the point A, the graph of the function down to negative infinity. This vertical line is a vertical asymptote. The equation of this line is x is equal to A. All the points on the line satisfy this equation. This is an infinite limit because the limit is infinity. But this limit is not an infinite limit because L is a finite number. This limit is just a normal limit. A sketch of this limit is here. As x approaches A, the graph approaches this open dot. The height of this open dot is L. Because the graph near the point A doesn't go up or go down to infinity. So this vertical line, this time, is not a vertical asymptote. Review 2. A limit of this form is called a limit at infinity. X approaches infinity. Function approaches a finite number. Here is a sketch of this limit. This limit is a limit at negative infinity. This horizontal line is a horizontal asymptote. The equation of this line is y is equal to L. Review number 3. A limit of this form is called an infinite limit at infinity. X approaches infinity. Function approaches infinity. Here, this is an infinite limit at positive infinity. The corresponding graph is this curve. In this case, the function has low horizontal asymptote, low vertical asymptote. Now, let me show you some examples about how to find horizontal asymptotes and vertical asymptotes. Example 1. Consider this function. 2 questions. Question A, find all the horizontal asymptotes of the function. Question B, find all the vertical asymptotes of the function. To find all the horizontal asymptotes, we need to compute the limit at positive infinity and the limit at negative infinity. Now let me compute the limit at positive infinity first. To find this limit by direct substitution, plug in infinity in x, but then we will have infinity over infinity. We don't know what is that. So we turn to simplify the function. Simplify the function so that the limit can be easily to tell. One standard approach to simplify a function in a limit at infinity is take out the highest power. In the numerator, the highest power is x squared. So take x squared out. We have this factorization. The highest power in the denominator is x squared. So take x squared out. Then we have this factorization. Now, cancel x squared from the top and from the bottom. We have this equation. Now, this limit should be easy to determine. As x approaches infinity, 9 divided by x should approach 0. And also this fraction, this quotient also approach 0. 5 over x should approach 0. 6 over x squared approaches 0. So this whole function, when x approaches infinity, this whole function will approach this number. This number is 1. Therefore, as x approaches infinity, function approaches 1. In graph, the graph of the function is getting closer and closer to this horizontal line. The height of this horizontal line is 1. Therefore, this horizontal line is a horizontal asymptote. The equation of this horizontal line is y is equal to 1. To see whether or not the function has a second horizontal asymptote, this time I compute the limit at negative infinity. To find this limit, again, I take out the highest power from the top and from the bottom. Then I have this equation. Cancel out x squared. Then I have this equation. Now, this limit should be easy to tell. X is approaching negative infinity. Therefore, 9 over x is approaching 0. 14 over x squared is approaching 0. 5 over x and 6 over x squared, they also approach 0. So this function, this whole function, is approaching this number. This number is 1. So as x approaches negative infinity, the graph of the function also approach this same horizontal line. Therefore, the function in this example has only one horizontal asymptote. The equation of this horizontal line is y equals 1. Now, part B. Find all the vertical asymptotes of the function. At the vertical asymptote, function approaches infinity. To answer part B, there is one important remark. Remember this remark. A vertical asymptote is only likely to occur at a point A where the denominator is 0. Because only when the denominator is 0, the function is likely to be infinity. Because of this remark, we set the denominator of the function to 0. The function is this. Set denominator to 0. Denominator to 0. Then solve this quadratic equation by quadratic formula. The two roots of this equation is 2 and 3. If the function has a vertical asymptote, that vertical asymptote can only appear at one of these 2 points. Now, compute the limit at each of these 2 points. If the limit is infinity, then the function has a vertical asymptote at that point. If the limit is a finite number, then the function has low vertical asymptote at that point. For the left-hand side limit at point 2, by direct substitution, we plug in 2 in x, but then we have 0 over 0. We don't know what is 0 over 0. So to determine the limit, we need to simplify the function. Factor the polynomial on the top, we get x minus 2 times x minus 7. Factor the polynomial at the bottom, we get x minus 2 times x minus 3. Cancel x minus 2. Then we have this limit. Now, plug in 2 in x, then the limit is equal to 5. So when x approaches 2 from the left side, the graph approaches 5. This point, the height is 5. Similarly, when x approaches 2 from the right side, the limit is also 5. Also 5. The graph approaches the same point. Because at point 2, the graph doesn't go up to positive infinity or go down to negative infinity. So this vertical line is not a vertical asymptote. In other words, the function in this example, at point 2, the function has low vertical asymptote. Now, we turn to compute the limits at point 3. For the left-hand side limit at point 3, we plug in the number 3 in x. Then the limit is equal to this number. This number is -4 divided by 0. A non-zero number divided by 0 is infinity, either positive or negative. To determine positive or negative, we pick a point very close to 3, but on the left side. Say, pick 2.99 and evaluate the function value at 2.99. Then we get function value is positive. So when x is close to 3 and on the right side and on the left side, function value is positive. Therefore, this infinity is a positive infinity. So when x approaches 3 from the left side, function approaches infinity. So on the left to the point 3, the graph goes up to positive infinity. Therefore, this vertical line is a vertical asymptote. Similarly, we can find that the right-hand side limit at the point 3 is negative infinity. Actually, to say that this vertical line is a vertical asymptote, one of the left-hand side limit and the right-hand side limit is infinity is sufficient. This example 1, has a second solution. The second solution is simpler than the solution that I just presented. Recall that when I answer part B, I set the denominator of the function to 0 and set the denominator to 0 and solve this equation, and we obtain 2 points, 2 and 3. If the function has a vertical asymptote, then the vertical asymptote can only appear at one of these 2 points. After some work, we found that at point 2, the function has low vertical asymptote because these 2 limits both are finite, not infinity. In the second solution, I simplify the function first before I answer these 2 questions. In this way, the number 2, where the function has low vertical asymptote, will be dropped automatically. Here is the second solution. Before answering part A and part B of the example, I simplify the function first. Factor out the 2 polynomials, then I have this equation. Cancel x minus 2 from the top and from the bottom. Then the function f is simplified to this function. Now, I answer part A. Find all the horizontal asymptotes. To find all the horizontal asymptotes, we need to compute the limit at positive infinity and the limit at negative infinity. For the limit at positive infinity, I take the highest powers out. I take x out. Then I have this equation. Cancel x, then I have this equation. Now, this limit should be easy to tell. As x approaches infinity, 7 over x, 3 over x, they approach 0. So this limit is this number. This number is 1. So as x approaches positive infinity, function value approaches 1. Therefore, 1 is a horizontal asymptote. Similarly, we can determine the limit at negative infinity. It is also 1. So the function in this example has 1 horizontal asymptote. The equation of the horizontal asymptote is y equals 1. Part B. Find all the vertical asymptotes of the function f. Because a vertical asymptote is only likely to occur at a point where the denominator is 0. I set the denominator to 0 and solve this equation. Then I have 1 point, point 3. If the function has a vertical asymptote, then the vertical asymptote can only appear at this point. Now, to determine whether or not the function has a vertical asymptote at point 3, we need to compute limits at point 3. If one of the limits is infinity, then at point 3, the function has a vertical asymptote. If none of the limits is infinity, then the function has low vertical asymptote at point 3. Now, compute the left-hand side limit at point 3. By direct substitution, to find the limit, plug in number 3 in x, then the limit is this number. This number is negative 4 over 0. Non-zero number over 0 is infinity, either positive or negative. To determine positive infinity or negative infinity, I pick a point very close to 3, but on the left side. Say pick 2.99, then evaluate the function value at 2.99. Then we get the function value is positive. So when x is close to 3 from the left side, function value is positive. So the limit is positive infinity. The limit is positive infinity. So therefore, this vertical line is a vertical asymptote. The equation of this vertical line is x equals the number 3. Example 2. Consider this function. Part A, compute the limit at positive infinity and the limit at negative infinity. Then identify any horizontal asymptotes. Part B, find all vertical asymptotes. For each value of A, determine right-hand side limit, left-hand side limit, and both side limit. I adopt the second solution to example 1 to solve this example. Before answering the questions in part A and part B, I simplify the function first. Factor the polynomials on the top and at the bottom. Then I get this equation. Cancel x minus a. Then the function f is simplified to this function. Function f and this function, they are equal everywhere except at 2 points. When x is 0, function f is not computable. When x is 8, function value is not computable. So function f and x minus 2, these two functions, they are equal everywhere except at 0 and at 8. This is the graph of function f. At 0, I place an open dot. At 8, I place an open dot. This is a straight line, the line of x minus 2. After we simplify the function, now we answer part A and part B. Part A. It's easy to see that the limit at positive infinity is positive infinity, and the limit at negative infinity is negative infinity. Because low finite number, so the function has low horizontal asymptotes. Part B, 5 vertical asymptotes. Because the function has low denominator, the function has low vertical asymptote. Example 3. Consider this function. Part A, compute the limit at positive infinity and the limit at negative infinity. Then identify any horizontal asymptotes. Part B, 5 vertical asymptotes. For each vertical asymptote, compute left-hand limit and right-hand limit. Before answering the questions in part A and part B, I simplify the function. By factorization, the function f is this function. Cancel the factor x and the factor x plus 2. Then the function f is this function. Now, part A. Compute the limit at positive infinity. The function f now is this function. Take out the highest power x on the top. Then we have this equation. Cancel x. Then we have this equation. as x approaches positive infinity, 3 over x approaches 0. So this limit is this number. This number is 2. Therefore, the horizontal line passing 2 is a horizontal asymptote. Similarly, the limit at negative infinity is also 2. So the function in this example has only one horizontal asymptote. Only one horizontal asymptote. And the equation of this line is y is equal to 2. Part B. To find vertical asymptotes, we set the denominator of the function to 0. Now the function is this function. Set x to 0, then we have a single point, 0. If the function f has a vertical asymptote, then the vertical asymptote can only appear at 0. Now we compute left-hand limit as 0. By direct substitution, plugging 0 in x, then the left-hand limit is this number. This number is 6 divided by 0. It is an infinity, either positive or negative infinity. To determine the sign of the infinity, I pick a point very close to 0, but on the left side. Say, pick negative 0.01. Evaluate the function value at negative 0.01, then we get the function value is negative. So when x very close to 0, but on the left side, function is negative. Therefore, this infinity is a negative infinity. So we have, as x approaches 0 from the left side, function approaches negative infinity. So therefore 0, x is equal to 0. This vertical line is a vertical asymptote. This vertical line actually is the y-axis. According to Part B, we are required to compute left-hand limit and also the right-hand limit. We are done with the left-hand limit. Now, let's compute the right-hand limit at 0. By direct substitution, plugging 0 in x, then the right-hand limit is this number. It is 6 over 0. 6 over 0 is either positive or negative infinity. To determine the sign, I pick a point close to 0, but on the right side. Say I pick 0.01. Evaluate the function value at 0.01, then I get 602, positive. So when x is close to 0, but on the right side, function is positive. Therefore, this limit is a positive infinity. So as x approaches 0 from the right side, function approaches positive infinity. This limit also shows that the y-axis is a vertical asymptote.